welcome back. Hope you all managed to get some fun during this fall break. So first, some admin stuff. Your midterm project is going to be due pretty soon. It's due, there's a typo over here. It should be due Sunday, 29th October at 8 p.m. The main goals for the midterm report is to experiment with your data set, try out some of the recent state-of-the-art approaches. Each team of N people are expected to have N-1 baseline models. But more importantly, after you run these state-of-the-art baseline models, is your error analysis. And we covered a couple of examples of error analysis 2 weeks ago, including looking at data points which a model fails on, simple cases which you expect the model to not work on, different ways of doing ablation studies, perturbing the model, testing the robustness of the model, and so on. So bulk of the report should be on discussing the errors of the model and discussing several proposed ideas towards fixing these errors, towards improving these models by fixing these errors. And again, based on that, you should be discussing your research ideas, right? Different research ideas to improve the errors that you found in the model. Again, N students should have N-1 research ideas. And ideally, all of these ideas should be around one of the multimodal challenges we discussed in class, whether it's representation, alignment, generation, and so on. And it's okay if at most one idea can be unimodal in nature, but most of them should be multimodal ideas. Yes?
Do we have to implement all the three state-of-the-art baselines, or like suppose if we have the outputs already for one of the models?
Yeah, good question. You don't have to re-implement them. You can use code wherever available, but you should be running them, analyzing the outputs carefully, and so on. Okay? And just a recap, this is a typo. This should be Sunday, 29th of October. Okay? For all the latest instructions are on Piazza. Yes? Right. Oh yeah. So one important thing about baselines. Baselines are not necessarily restricted to papers published only on that data set. Right? Let's say this data set came out last week. It doesn't mean that there's no baselines on this data set, right? There's a lot of established research on similar problems, including the ones we talk about in class. So it's a new data set for fusion, for example, you're expected to try out early fusion, late fusion, dynamic fusion, all the standard fusion methods we talk about in class, even though people may not have published results of those baselines on that new data set. Okay. So yes, data set being new and not many papers on a data set doesn't mean that there aren't possible baselines to be run. They have been tested on similar data sets that are tackling similar challenges.
So if the data set is too large, can we just use a sub data set to run baselines?
Yes, good question. You may use a subset, but you should be consistent between experiments. So you're always using the same subset so that you can draw conclusions by comparing models. And of course, the most important part of the discussion, how is the error analysis and how is that also inspiring your proposed research ideas? Yes? It's a exceptional reason why you want to do zero shot. So in other words, you should, to the best of your ability, test out the baselines for that new data set under the circumstances their data set enables, right? So it's a data set that was proposed for supervised learning, for example, you definitely have to fine tune it. If a data set was proposed for zero shot learning because there just isn't any training data you can get, then it should be fine to zero shot. But it should be kind of justified your motivation for doing that experimental setup. Yes? To do zero shot, because it has this open vocabulary setting where you can classify any categories, right? But of course, if I want to do some image captioning tasks, say in like healthcare, and I want to apply clip, I'm going to fine tune it, right? So, I mean, you have to motivate why, like my first thought would be to fine tune it so that it gets better. But if there's a circumstance where you think zero shot is sufficient, then you have to motivate that. Cool. Any other questions? So that's our report. The presentations will be the week following the report. The report is due on Sunday. The presentations will be on Tuesday and Thursday next week. Next week. And the main objective is to present your findings from the error analysis and your proposed research ideas and get feedback from classmates. And there's some guidelines on how long they should be. Every student is expected to present at least a little bit for the presentation, so you should be rotating among yourselves. And following each presentation, the audience will be given a little bit of time to write down their feedback on like a Google Doc, and they'll be shared with the team members afterwards. So all presentations should be done from the same laptop. There's going to be some instructions on Piazza for you to submit all your slides the day before, ideally in Google Slides. Make sure to be on time, follow the guidelines for how long you're supposed to present, because we're going to kind of stack the whole class up with presentations back to back. And they should all be done in person. Everyone should present. And we're also going to release a schedule for who's presenting on Tuesday and who's presenting on Thursday, but you should be in class for both sessions regardless, right? Because you have to give feedback for the students who are presenting if you're not presenting. Just check the policy on Piazza, but I don't know if there's late days for the presentations. I think they should. Presentations have to be done next Tuesday and Thursday. There's no way we can reschedule them. There may be late days for the report. Okay, some suggestions. Don't spend all the presentation just talking about your existing results. We want to save a good amount of time for the proposed research ideas, right? Especially don't explain the state-of-the-art baselines in detail, right? That's not necessary. We don't want you to just review existing papers, existing baselines. You should just be kind of citing a baseline, maybe like 1 or 2 sentences motivating why that baseline was chosen, what that baseline was designed to tackle, but spend a good amount of time on the experiments and the errors of that baseline and the proposed future ideas. Okay, so the focus should be on the proposed future ideas. Plan about 1 minute for each research idea and present them at a high level. Don't go into the details, present them at a high level so that the audience can give feedback and you're well motivating the idea from a high level. Again, don't spend too much time on the data set, on the tasks, on the related work. That should be just quick, 1 minute. All teammates should be involved, and ideally you want your slides to be 80% visual, right? Not text like this, but it should be mostly visual. And again, the grading scheme is on Piazza, but roughly there's 4 points for presentation that involves quality of the slides, motivation, quality of the research ideas, and in general presentation skills. And 1 point will be given to feedback. So if you're not presenting, you should be giving adequate feedback to the other groups who are presenting. We're going to judge that based on 1 point. Okay. Any questions? Any questions about the report and the presentations? There should be a Google Doc that we're going to hand out, and you're going to write it there. Great. Okay, so today we're going to talk about generation. That's the 4th challenge. We're going to talk a little bit about generation today and also more generation on Thursday. But if you recall, we've already talked about 3 challenges, right? We had 2 modalities, assuming elements in each modality. If you just have 1 element in one, like one element in the other, how do you learn representations that either fuse, coordinate, or factorize these elements? And the second big challenge was alignment, right? Considering multiple elements across modalities, how do you align one group of elements in one modality to one group of elements in the other modality, respecting the structure of the problem? The third challenge we talked about before fall break was primarily reasoning. So how do you do this compositionality problem in a principled way, taking into account the structure of the problem, the relationships between modalities, the inference, the external knowledge, and so on. And all 3 previous challenges were in the context of prediction, right? It was mostly about prediction, question answering. In this challenge, we're going to go towards generating modalities. That's why it's called generation. We're going to go from prediction to learning a generative process that is able to allow me to generate more modalities that ideally reflects the interactions that the modality contains and the coherence within each modality by themselves. And there's 3 big paradigms we're going to talk about, mostly application-driven. The first big paradigm is summarization. If you have a lot of data, a lot of multimodal data, how can I summarize it to get the most salient, most important features? So one classic example is, if you have a very long video, for example, can you summarize it with the most important image and maybe one short description that summarizes what's happening in the video? So in other words, you're going from a large amount of information to a smaller amount of information. The second big paradigm is translation, right? Maintaining the information content, but semantically translating from one modality to the other. So right here, you have an image, and your goal is to caption that image. You want to caption all the information that's in the image, nothing more, nothing less, ideally. So you want to maintain the information content by translating from one modality to the other. And finally, creation. Creation is relatively harder, much less work done on creation, but the goal is to go from small amount of information content to more. If I have latent variables, for example, representing some concept, if I have maybe one image at the beginning, can I use that to generate more modalities? For example, a whole video corresponding to that image. Perhaps even with aligned audio, aligned transcripts of that video, all just starting from a single image or from some latent variable representing some concept. Right, so in this case, the goal is to expand your information content, go from less information or smaller dimension of information to much more information. So underlying generation, there's typically two dimensions we want to consider. One dimension is how the information content is changing. Right? And we saw that information content can be reduced, can be maintained, could be expanded. And when we talk about information content, you want to rethink connections between modalities, right? This information content can be reduced, maintained, or expanded because there are underlying connections between them. Right? And recall that these connections can typically be because of associations, because of actual correspondences. So for example, if I want to do image captioning from an image to its caption, I want to maintain information content by looking at the semantic connections that exist between my image and my caption. Right? I know that this is an image of a laptop. I want to describe it as a caption with the word laptop in it. So maintaining information content is an example of exploiting these correspondences between image and text. Of course, if you want to reduce information content or you want to expand information content, you're still looking at the connections between modalities. It's just, do I reduce the number of connections if I want to summarize, or do I expand the number of connections if I want to increase information content? So one dimension underlying generation is the underlying connections between modalities. The other big dimension that we're typically going to categorize different types of work is the generative process itself. The generative process can be more example-based or can be actual generative based on generative models. Today, we're going to talk a bit more example-based. By example-based, what happens is that you have a dictionary of translations. For example, you have an image and its corresponding caption. You have another image and its corresponding caption, and you have a huge data set of images and their corresponding captions. If I give you a new image, you're going to search for the nearest image and just output that corresponding caption. So typically, this is called a dictionary of translations. Example-based approaches are limited to items in a dictionary, so it's more retrieval-based. The good thing is that you're guaranteed to give good captions if your dictionary is good. The disadvantage of this is that you're obviously limited to what you have in your dictionary. It can't generalize to completely new cases. The other big paradigm is more generative. In this case, you still have a dictionary of translations, but you're going to use a dictionary of translations to learn a generative model that takes in one and generates the other. That's during training. And finally, during testing, you're going to give it a new input. You're going to pass it through a generative model. And because you're passing it through a generative model, it's going to work for any arbitrary new input. It does not have to be limited to the dictionary that you've seen during training. Right? That's a good thing. The bad thing is that it can hallucinate. It can generate content that is not good. Most of the work in your diffusion models, generative models fall into this generative category. Okay, so typically there's these two dimensions you have to consider in any problem. How does my information content change? And therefore, should I exploit my connections exactly? Should I reduce the connections between modalities? Should I increase the connections between modalities? And the second dimension is what type of generative paradigm do I use? Do I do something like retrieving, which is more example-based, or do I actually train a generative model from scratch, which is more generative-based? And both have their pros and cons. Okay. So to see these two dimensions in action, the first case, I'm going to talk about summarization. In the first case, when the information content is reduced, right? You want to reduce the amount of information content by compressing your modalities such that the ones that are connected is smaller. And one example of summarization is video summarization. So let's say you have a very long video. For example, this is a huge, very long video of someone cooking, and you have a transcript of the person cooking, explaining what they're doing, the different steps. So there's a lot of connections between them, right? is going to be connected based on like the first instruction, how to make a Spanish omelet. You're going to start by dicing a little bit of peppers, and you have the video of people dicing peppers. And it's going to go on all the way through the entire video. Summarization will try to identify the cross-modal interactions and summarize them. So it's just summarizing to a small summary. For example, cutting peppers, making a Spanish omelet, making a Cuban breakfast as part of the omelet. Okay, so that's an example of summarization. So we're here. How the model actually does it is that you have a lot of elements in your modalities, a very long video. They're first summarizing and learning a few representations. That's much slower in dimension than the original video. And using that, it's actually defining a generative model that actually auto-regressively predicts word by word what the summary should be. Right, so based on information content that is reducing by capturing only the cross-modal interactions that are actually overlapping with each other. And in terms of the second dimension, a generative process, this method was done through a generative model, an auto-regressive model that actually predicts word by word. So in the second case, where you're trying to maintain information content, the classic example is translation. And you've probably seen some of these cool examples from DALL-E where you can take in description and generate diverse images based on the description, even though the description may seem nonsensical, right? So how these methods typically work at a very high level, we're going to talk about the details later into the lecture. But essentially how they work is that they start by training a variational autoencoder. And in this case, they're training a discrete variational autoencoder that takes in images and reconstructs these images. And this can be done at scale. This can be done without being limited to image and caption paired data. If you have a lot of images, you can just train a very good discrete variational autoencoder. We're saying discrete in this case because the hidden features in the middle of the variational autoencoder are limited to be 1 in k. So they're 1 in k set of discrete features instead of the continuous features that you're typically used to in VAEs. Once they've pre-trained this discrete variational autoencoder, they can then train a text-to-image model, but you're not going directly from the text to the image, you're going from text to these discrete features, right? And you can train a large transformer to do this, given some paired data. For example, the caption will go through a text encoder that will learn some text features, and a transformer will then auto-regressively predict the discrete image features corresponding to this input caption. And finally, you can then generate, right? The text comes in, you go through a transformer to your discrete image features. You can then pass it through the image decoder, or the decoder part of the VAE, to then generate the image for that input caption. Yes, but again, it goes back to this discussion of whether generative process should be example-based or fully generative, right? In this case, they showed that a more example-based, where the examples are your discrete features within this discrete VAE latent space. And this actually was performed better than the generative case. So there's pros and cons to both. The biggest pro of the generative case is that you can generalize to anything, right? You're in continuous space, you can generalize to anything. The disadvantage is that you can then hallucinate. You have this mode collapse problem where if you don't see a set of continuous features for a particular input, it can just collapse. It won't be able to give what your desired output should be. The good thing about the example base is that it mitigates that. It mitigates the fact that you may not have seen any feature because you're guaranteed to retrieve from a discrete feature that you've seen in this dictionary, right? The disadvantage obviously is that if this dictionary is not big enough, it's not going to be able to cover all things that you want to generate. Okay, but same thing, right? The 2 dimensions. One is the content. In this case, the content is maintained because you're only capturing the corresponding cross-modal interactions that have the exact same meaning. And the second dimension, a generative process, is more exemplar-based, using this discrete latent space. The VAE took in a bunch of images just by itself. It doesn't have to be paired with the caption, so just the image. And you pre-train an image encoder into the discrete space, and you train the decoder back to the original image. So this can be pre-trained separately. So you can pre-train the image encoder and decoder. Afterwards, now you have some corresponding caption and the image. You're going to use this pipeline where the caption goes through a text encoder and maps it into the discrete VAE feature space. and then through the text image decoder, it's going to decode the image. And this can be done for other image text pairs where you actually have the image and the description pairs. Okay. But again, in any of these models, you got to think of two paradigms. One, how do I maintain how do I change the information content? In this case, we're maintaining the information content using paired data, where the image and text meanings are corresponding to each other. And what type of generative process do I do? In this case, it was a discrete VAE. That was a more exemplar-based generative process. And of course, there was DALL-E 2, which improved DALL-E quite a bit, with some main differences. One big difference is that they didn't train a discrete VAE anymore. It wasn't a discrete VAE trained from scratch, but rather it was the clip encoder. Right? We saw clip back when we were talking about coordinated representations, right? The image, you learn a feature, you text, you learn a feature, and you're going to align them using some contrastive learning so that the image features and the text features are coordinated with each other. And obviously, that makes for a very good encoder, not only because it's able to encode images into semantic space, but also because these image embeddings that you get are already coordinated with your caption embeddings, right? So they're much closer in alignment to the captions. So you can use a clip encoder in place of a discrete VAE encoder. This clip encoder can be trained a large amount of data. When you get a caption, you can again pass it through a text encoder and try to map it into the clip image embedding space. They found a diffusion model works better for this. We're going to go into details about diffusion model soon. Next sector. And once you've mapped your images through a text encoder into your clip image embedding space, you can then use a diffusion model from the embedding space to generate images. Right? And again, these diffusion models work much better than your VAE decoders. So we're going to talk about diffusion models in more detail on Thursday. Not exactly contrastive learning. So clip encoder has been pre-trained through contrastive learning, right? But in this part, we're literally doing translation in the sense that I take a caption, I'm going to get the token embeddings. I'm going to use the token embeddings to predict the image embeddings. Like literally, there may be 3 of them. And circle is the image embeddings that you want to predict. So you're going to literally translate from the text embeddings to the image. Be exemplar, right? Very good. So in this case, the content is still you're maintaining content. You're maintaining content because clip similarity enables you to capture correspondences between image and text with the exact same information content. But in terms of the generation, it's not exemplar anymore. It's fully generative. It's fully generative using, in this case, diffusion models. Right. So again, as you see, many models, they all fall under like these 2 considerations. The first dimension is how do you want to maintain, increase, or reduce your information content, and how are you going to do that, whether it's through paired data, whether it's through like a pre-trained model like Clip that enables you to maintain information content. That's the first consideration. And the second consideration is what type of generative model do you use? Is it more exemplar-based, a dictionary? Is it more generative-based? And we're going to talk about several classes of generative models today and on Thursday. Okay, and of course, that gets really good results, right? You can give very cool descriptive captions, probably nothing as seen in a training set before. An astronaut riding a horse in the style of Andy Warhol, or a bowl of image that is a portal to another dimension as digital art. And it's still able to generate realistic images. It's able to leverage the compositionality of the bowl of soup that is probably seen. Digital art is probably seen, but not in that exact combination, right? So it's able to exploit compositionality and generate these images with arbitrary combinations of input tokens. So another cool example I want to highlight, a lot of these translations, obviously nowadays you have these text to image, image to text translation. That's really cool. But another big application for generation is to create these virtual humans, right, for entertainment. Now, you've probably seen what these are like from movies, and these are kind of a virtual human example of them. And you've probably seen a lot of games where you have these like virtual characters based off of real world characters in movies, right? So over there, they're also doing some translation. So I'll play this video. In the input, you're taking in the transcripts and the audio, and you're trying to predict this virtual human avatar trying to speak, the speaker speak, and also the listener listen and have the facial expressions of the listener in the same way that corresponds to the input video.
Your Honor, I'd like to ask for a recess. I'd like an answer to the question, Judge.
The court will wait for an answer.
If Lieutenant Kendrick gave an order that Santiago wasn't to be touched, why did he have to be transferred? Lieutenant Kendrick ordered the code red, didn't he? Because that's what you told Lieutenant Kendrick to do. Object! What you cut these guys loose, Your Honor! You have more than the phony transfer. Your Honor, you doctored the logbook.
Consider yourself in contempt.
Colonel Jessup, did you order the code red?
You don't have to answer that question.
I'll answer the question. You want answers? I think I'm entitled. You want answers? I want the truth. You can't handle the truth.
Yeah, that's translation. So a lot of big applications in movies, in graphics, in video games, and so on. Okay, another cool example of translation. Again, this is trying to maintain information content as much as possible by going from these descriptions of physical activities to actually rendering these like stick figures doing those activities. So a person jogs a few steps. A person steps forward, then turns around and steps forward again. A kneeling person raises their arms to the sides and stands up. Yeah. That's also translation. Okay, and finally creation. Right? Creation, the goal is to start from a small amount of modalities. There may be some connections between them to expanding the amount of modalities you have. Right, going to higher information content, but as you go to higher information content, you still want these modalities to be coherent. Right, if this is text with 3 words, you want to go with more words, you still want a text to be coherent. If this is a video with 3 frames, you want to go to a longer video, you still want the video frames internally to be coherent, but also you want the video and text to ideally still be connected with each other, still maintain those connections, still correspond to each other. And of course, creation is very difficult, right? If you want to simultaneously generate multiple modalities to increase information while maintaining coherence within and across modalities, this is very difficult, right? I've not seen any compelling examples able to do this yet, but probably a lot of people are working on this nowadays. So you can start from many things. You can start with latent variables. You can start with maybe just an original image. And ideally, you want to generate, for example, a video corresponding to that starter image, captions of it, sounds also corresponding to the videos and descriptions. And again, there's 2 things. You want to maintain the connections and interactions between the modalities, and also some structure across your modalities. So everything that we've talked about in alignment and reasoning, that there's temporal structure, there's causal structure within a modality should also be maintained. And one example, some initial attempts, usually these factorized versions of generative models are very useful. So in this case, I'm showing a model with 3 factors, one corresponding to the first modality, one corresponding to the second modality, and the middle one corresponding to the label, right? So in this case, if I take the style of the first modality, that tells me how my 9 should be written. The feature corresponding to a label, it tells me that this is actually a 9. And likewise, I can pair that with the style in the second modality, then I should get a 9 written in a different way. Right. So if I have these, and if I take the latent variable corresponding to the digit, that should enable me to predict the actual number I have. So of course, this is at a small scale, but eventually you also probably need to build some factorized version of these generative models. They're able to control what is unique in the first modality, what is unique in the second modality, and what are the connections between your modalities. Right. So 2 corresponding to unimodal unique information, 1 corresponding to the interactions between both modalities. And you can do that at scale. So you can fix the latent variable corresponding to the label, fix that at 5. And then you can vary the first latent variable. That will change the style of 5 being written in the first modality. you can then change the second latent variable that will control the style of 5 being written in the second modality. And likewise, if you fix the style of the first and change the digit, you can have the same style and different digits within that same style. Likewise, I fix the style in the second modality, I can change the digits being written in that second modality. So that's just creation at a very small scale, right? You're starting from one image. In fact, you start from latent variables, and you can generate arbitrary amounts of data, but still corresponding to whether the style is the same or the content, the digit is the same. So in this case, how does the content change? I'm going to increase the content based on these factorized representations, because like factorized representations capture information unique and also common to both modalities. I can change one and keep the other constant to arbitrarily get large amount of data. In this case, the generation is a generative model, is a EAE decoder that goes from these latent variables to your outputs. All right, so that's a high-level summary of generation. 3 application paradigms of summarizing, translating, or creating more data based on whether you're reducing, maintaining, or expanding information content. That's the first dimension. And the second dimension is whether what exact type of generative model you're using. Is it more example-based or is it actual generative model? And before I get into some of the technical details for generation, some concerns, right? Probably some of you have seen this. It's very hard to evaluate generative models because you're no longer classifying or regressing something. You have well-established classification or regression metrics. You're generating things. It's really hard to evaluate. And one difficulty behind difficulty of evaluating is the fact that you can also generate things that have ethical concerns. For example, you can generate, in this case, it was a generative model that tried to do super resolution. So you start from a blurry image, smaller in dimension, to go to a more fine-grained image, high resolution, and ended up turning Obama slightly white, right? So that's an example of a racial bias that can happen in generative models. Language models, even back to GPT-2, were able to memorize text and output social security numbers, phone numbers, actual addresses of people. And of course, these language models can also very easily generate stereotypes or even worse, bad content based on different genders and races, right? So again, lots of difficulties in evaluating and also lots of ethical concerns behind these generative models, right? So lots of open challenges over here. Okay, any questions about the high level behind generation? We've not really talked about technical details about the generative models and the multimodal part yet, but this is meant to give a more high level overview of the applications and the concepts behind generation. Okay, great. So just actually a few more applications. When we think of generation, I think most of you would think of image captioning to begin with, right? And I just want to give an example of how image captioning as an application that we all want to work on or we all want to improve can be seen from the lens of either summarization, translation, or creation, right? So you can think of captioning as summarization. A lot of the initial work in image captioning was actually done this way by first taking an image, using object detectors to detect what objects are in the image. For example, pet, sleep and ground, dog, sleep and ground. So that's really going from high dimensional images to just summarizing using an object detector the most salient object features, right? Maybe there's 3 or 4 of them. Once you've done that summarization, I can then use a template to put these object categories together into a coherent sentence, either through a template, but nowadays you can think of doing it using a language model, right? So that's a way of doing captioning as summarization. The biggest benefit here is that you're guaranteed that you're not going to hallucinate. Once you've captured the objects that you desire to that you want to capture, the only thing the generative model is doing is just filling in these objects into a coherent sentence. You can also view captioning as translation. So in this case, you're more maintaining the information content. You're not just summarizing into like 3 objects that represents the entire image, but rather trying to more closely match all the information within the image. So this is some form of scene graph the scene graph basically captures all the objects in the image, all their relationships with other objects, and all their attributes, right? So attributes and prepositions. And once you've done that, you can then, again, you're maintaining the information content, but translating that to a sentence where you're writing all of this scene graph information, the objects, relationships with other objects, and the attributes in a coherent sentence. So that was baby talk paper, a little bit after the first one. And finally, nowadays, you can also view captioning as generation, where you start with an image and you start by generating much more content than what the original image had. So that was visual storytelling, right? You want to use the image as a starting point to tell a story that may go beyond the original image. And one cool thing that you can also do is that you can take in multiple images instead of independently generating captions for them. Have the model treat these images as a sequence of, in some sense, comic panels, so parts of the story, and in the end, generate a very long story that follows coherently from one image to the next, right? So in this case, you can tell that this is a person playing soccer, and afterwards they're playing, but the soccer ball, they kicked it too hard, the soccer ball became stuck on the roof of the house, right? So it's more coherent than just describing the image and saying this is a soccer ball on the top of the house, right? It actually leveraged the fact that it was a person playing soccer, and because they kicked it too hard, they became stuck at the top of a house. Yes, clear. I don't know if they've done all the experiments with temperature. Also, you want to think that the initial version of this was created before like today's language models and like, how temperature affects today's language models, but it will be good to maybe revisit some of these, right? As much as these language models are good, they still struggle with exact conditional generation, right? It's still hard to get them to focus exactly on an image and only the image and not say either too many things or too few things. Yeah, but it's a good kind of research question to investigate. Great. And generation is also very data dependent, right? It really depends on what data you're collecting. Some of the initial good data sets were like, for example, Flickr. Flickr data sets are used for image caption retrieval, but can also use train image caption models on them. And a lot of the captions here are very short and very to the point. So a graying man in a suit is perplexed at a business meeting. So very short and to the point. So if you train models based on these Flickr data, you're probably going to get similar distribution of captions on as these, right? So it's going to work well for images with the objects very clear in the foreground, and the captions are short and directly describe what's happening in the foreground. Localized narratives is a much richer data set that can also be used for image captioning. In fact, the other good thing is that you have these red, yellow, green. These are the mouse traces. The mouse traces that the annotators who are annotating the captions for the data, they're actually using a mouse and saying, okay, I'm looking at this part in red. I'm looking at this part in red. Here's what I'm seeing, and here's what I'm captioning. They're typing the captions. And afterwards, they move to another part of the image. In purple, for example, they're going to put their mouse over there, and they're also describing the captions for that part of the image. So with localized narratives, you can train much richer visual storytelling models, because these captions tend to be very long and it tend to tell very descriptive stories of the image. And you can also train more localized versions of these image captioning models. So not just one caption for the entire image, but you can train the models to take in also like a bounding box or like an attention map on the image and have it generate a caption based on that. So it really depends on your data. And some more complex examples, we've seen video summarization. That's a big application, but it involves much more complex inputs than just the image. Nowadays, folks are also working on sign language translation. You can take in a video of people speaking in sign language. Can you translate that to what the people are actually saying, right? That has benefits for people who have disabilities and have to rely on sign language. And finally, you can also apply generation for reinforcement learning. Right, we saw reinforcement learning the week before fall break. And there's examples of this where you have a robot that's trying to navigate a house. Right, naturally navigating a house involves multiple steps. Right, for example, you want to go to the refrigerator, pick up an apple, give it to the person. It involves multiple steps, such as actually going to the refrigerator, opening the door, picking up the apple, closing the door, and so on. It's going to be quite hard for an agent to figure it out by themselves. Right, you're going to need to do a lot of trial and error before the agent actually does that by themselves. one thing you can do is you can use a generative model to generate instructions, right? To go from the scene, the state, and the description of the task, and generate the instructions step by step that can then be used by the agent to follow these instructions step by step, give it intermediate rewards whenever it executes an intermediate step correctly, and that will help the agent a lot more when it comes to solving a task. So generating instructions can also be seen as a generation problem. Great. Okay, so now into some of the technical details about generation. In all of these generative models, it's usually modeling P of X, where X is some modality, can be text, images, videos, multimodal data. And usually there's two things we're going to do. Three things actually, two of which are directly applied to generation. First, given a sample X, can I evaluate P of X? So how good, how likely this current sample should appear given my generative model? High P of X. Realistic data should have high P of X, and unrealistic data should have low P of X. Typically, using that, we also want to be able to sample new X given P of X, right? So if P of X is my distribution of images, I should be able to sample high likelihood images. And of course, most of the time when we train a generative model, it can also be used for unsupervised representation learning. The P of X that you learn, which assigns high likelihood to realistic data and low likelihood to unrealistic data, should also be very useful in making predictions on this data. In a lot of times, we also care about P of X given C, right? We're not doing free-form generation of any image or any text. We're typically doing generation, for example, via translation, translating from image to text. In that case, I'm doing P of X given C, where image is the input coming in. That's a condition to the generative model. And X given C is the text caption given this original input image. So we typically call this conditional generation, where C can be any category. It can also be a different modality entirely. And sometimes we also care about P of X2 given X1 and C. Sometimes I might have an image to begin with, and C is perhaps some change in language, some way to edit the image, and I output a new image that respects the original image X1, and also respecting the change in language, in the style as given by language, right? This is a great question. There's no established answer. That's why you hear people talking about AI safety, language model safety. There is no established answer yet, but you've probably seen several paradigms, right? One of the most popular is to train a model on whatever, all the data, but do some post hoc filtering. So nowadays, OpenAI is probably getting a lot of people to just annotate which are good, which are bad, which have biases, and so on. It's probably using a lot of manual and automatic filters as well. Automatic filters for certain words that it shouldn't generate, for certain numbers or things that look like addresses. Probably a lot of filtering that goes on afterwards. You can also think of kind of ways to mitigate bias earlier in the pipeline, including the data you train a model on. How do you remove biases from that? There's some work in it, but it tends to be not super scalable, especially as you want to train on more data, right? Because if you want to train on the whole internet, it's going to be really hard to do this filtering. If you're training on a smaller data set of just images and captions, you might have some ways to filter. So yeah, just probably different stages in the pipeline. I mean, some people are also investigating, like in the modeling pipeline, the modeling step, how do I mitigate biases using different training objectives, using different ways to change the internal features that don't contain certain information. There's also work in unlearning. Like, so you have machine learning, which is to learn. There's also like unlearning, which some people are working on nowadays. How do you provably get a model to unlearn something? And the provably is very important because a lot of methods empirically seem to get the model to unlearn something. Like for example, adversarial training. Some people might have this. You can train a model not to predict something, but to adversarially predict something. It means get the accuracy as low as possible on predicting a task. It seems like that should allow you to unlearn something, but people show that it's kind of hiding the information instead of unlearning the information. It's hiding the information, and you can still get the information out of the model using some other way, even though it's unlearned in this way. So yeah, a bunch of work. I'll probably put some references on Piazza, but there's no established solution yet. It's something that you should always consider when working on generative models. Yes. There's a bunch of evaluation benchmarks for bias, right? So language models, whether they are like gender bias, racial bias, and so on, essentially they take in the form of it's usually comparative, right? So you have like, for example, this prompt with this certain race, and this prompt is this other race, and maybe this prompt is some other race. And ideally, you want the completions to not differ that much, right? Because if like the completion for one race is very different from the other races, that can be seen as one form of bias. So they usually follow the structure. But yeah, there's a bunch of references. Just search like social bias language models, or nowadays you have diffusion models, and you have like social bias, gender bias, and diffusion models. But it's still, I mean, there's always room for better benchmarks. I don't think any of the benchmarks are perfect. Right? Framework. Not that I know of. I mean, there's a bunch of individual benchmarks. But yeah, probably, I mean, in each of the individual benchmarks is probably testing for one aspect, right? For one aspect. And it's hard because there's just an unlimited number of things, especially if you go, like, we talk about the two ways of generation. One is more example based, one is more generative based, right? Like if you go to generative based, it's infinite number of things you can generate. Infinite number of words, completions, images. So that's why, and it's also an infinite number of things that a user could prompt. That's what makes it very difficult. Yeah, so there's no really established way to control generative models perfectly. Great. Yeah, but I'll try to put up some references on the more ethical side of things. Okay. So established way to evaluate generative models. Over here, like, this mostly has to be done by a human. It has to be done by human metrics, like human evaluation. There's some heuristics for automatic evaluation, including like the GAN score, inception score, things like that, but none of them are perfect. I mean, same question. Nowadays, how do you evaluate language models, right? You can create like huge group of benchmarks, and there's some people who do that, and you can evaluate your vision language models on like VQA, VCR, image captioning, all of them. You can tally 100 multimodal data sets, get them to evaluate, which is a way. And then the other way is just to like literally play around with it for like 10 minutes, 15 minutes. But there's no established way of evaluating it. So lots of these are good questions to work on.
So in this
Generative models we're going to talk about is auto-regressive models. In fact, all of these auto-regressive models, the language models, are generative models, right? They essentially model P of X by doing some factorization auto-regressively, right? So I'm going to generate the first token and then the second token, x1 given x0, x2 given x1 and x0. They're doing some form of factorization. And of course, language models are like this, generating one word after the other using this factorization. But a lot of these there are also image versions of this, right? You can generate pixels, images pixel by pixel. You can generate videos frame by frame. Any model that basically decomposes the problem into some sequential nature can be considered auto-regressive models. So we're going to first start by seeing how we can build. We're not going to talk about building auto-regressive models. Most of these are pre-trained. We're not going to go into much detail about it. But we're going to primarily talk about conditioning auto-regressive models, right? These language models only give P of X, which is just language, one prompt in language, and you continue the language. How can I actually condition them on images or condition them on any other modality that you want to translate into language? So there's several ways of doing this. Some of them are simpler than the others, but one way of doing it, which is actually quite simple, is to do something like prefix tuning. So I have over here P of X, my language model, that takes in one word and repeatedly generates the next. That's my P of X. It's big, it's pre-trained, I'm going to keep it frozen, okay? And all I can do is I can take in an image or any other modality that I want to condition these language models on as an input. So over here, image with these red triangles depicting the image, and I can train an adapter, right? This adapter is essentially a model that takes an image, raw image, or maybe you can start from image features, and you bring them into language model space, right? So that it can be seen and processed in the same way as these language model tokens, right? So we call these adapters. Usually these adapters are much smaller than the language model itself. It can be as simple as a linear mapping that takes in pre-extracted image features from a vision model, a linear mapping into language model token embedding space. It can be as simple as that, and people find that it works, right? So once you have this adapter and your pre-trained model, what you have subsequently is a model that is both adapted, that has the power of the pre-trained language model, but also adapted with the context from the image features, right? And that can be seen as P of X given C. And what you're going to do is you're going to train this model that takes in the image and, for example, the caption, and auto-regressively predict word by word the next word in the caption, right? So ideally, this should let the model focus on the image, because it's going to be like the image is going to predict and then from the image, a small, and then it's going to predict a small red. So it's going to have to realize that the image has a red boat when you're predicting the words red and boat. Right? So ideally, this would allow the image, the model to focus on the image. And it works pretty well, right? You can give it a new image through the adapter. You can give it a new question through the pre-trained model. For example, what color is the car? And you output P of X given C, so blue, right? A completion for the language, condition on the image. So that's zero-shot VQA. You can also do one-shot outside knowledge VQA. One-shot because over here, you're giving like one. So the first question that you give is a task. So you're not giving any other examples of question-answer pairs. So that's like zero-shot. Over here is show that these authors show that you need to give one example first before letting it predict the answer. So the one example that I'm going to give is this image of an airplane and a question, who invented this? The Wright answer, the Wright brothers, and let it auto-regressively predict this word by word. That's my one-shot example. And then I can give it a new question. For example, image of the iPhone, a question, who invented this, with this A, and it's going to auto-regressively predict the answer, Steve Jobs. So that's an example of doing this for one shot. I think they found that one shot is needed to get this to work for outside knowledge. Somehow the one shot enables the language model to kind of start retrieving from this outside knowledge, like the Wikipedia that it had been trained on. I saw a question? Yeah. Outside knowledge in the context of the QA, but it's not outside knowledge to the language model, right? So language model probably seen all these Wikipedia pages about airplane, Wright brothers, iPhone. Just like one example is required to get the language model to start retrieving from that part of the context that has been trained on. Like zero shot, it could do directly. Oh, sorry, without outside knowledge, it could do zero shot exactly. But with the outside knowledge, these authors show that it needed one shot. Can't generate text. You need extensions of BERT to generate text. But the extensions of BERT that generate text are probably done using some, well, even if it's not auto-regressive, it has to evaluate P of X in some way, right? It has to kind of be a density model that here's the words that are more likely, or here's the sentences that are more likely to generate. Well, but auto-regressive is not a precursor to this. You can do these adapters for non-auto-regressive as well. The only important thing is that you have a P of X, whatever it is, auto-regressive, non-auto-regressive, and that's big, that's frozen. An adapter is what you want the model to condition on. So that can be small, that can be lightweight, and then you combine both, so that it's not just P of X, it's P of X condition on the adapter, and you have to train it in some way to actually get the model to look at the adapter, right, in some sense. Good question. I don't know exactly for that example. I would suggest checking out a paper. But I would assume if you're doing more like factual things with QA, you want to set a lower temperature. And you're doing more like storytelling, more like free-form storytelling generation, you would set a higher temperature and you will let it change. Of course, if the model is uncertain about something, like just literally doesn't know the answer, then if you set low temperature, it will also maybe like fluctuate. Yeah. Okay. And it can do a few other cool things. You can do this few shot image classification. So I'm going to give this apple as an image and have a caption saying this is a DAX. So I'm going to auto-regressively predict this is a DAX, where DAX is some nonsensical word. And I'm going to give it this orange and let it predict this is a Blicket while looking at the orange. And if I give it an apple in like a new orientation, you can ask what is it? And you should answer DAX. Right? So we can do this in some sense is the symbol binding problem. We're giving a new reference, a new symbolic reference, and it has to remember this new symbol reference using just one or two examples. Right? And you can do this as well. Some folks have also used this paradigm to do style transfer. So if I have a language, like the market was simulated by the deal, that was initial sentence I'm giving to the model, and my adapter, not only can it be image, it can be almost anything. It can be, in this case, stylistic attributes, right? Whether the model is in, whether a sentence is in present tense, past tense, whether it's like singular, plural, and it can change based on these transfer tokens. And then you have basically have methods that scale this up, right? Flamingo basically scales this up with a lot more data. And you can do all these longer forms of dialogue while also looking at the image. Right, so this is a cool example where you took the apple and it put a sticker on iPod, and it can answer, this is the apple with a sticker on it. And you can ask, what does the sticker say? The model will return the sticker says iPod, and so on. So same paradigm as the frozen language model with adapter. Flamingo just scales it up to get more data. So adapter has nothing to do with vision, right? So it's modality agnostic. What I've seen it used is any kind of model. You typically smaller in size. It can also be factorized, like for example what LoRa does. But any smaller model that you plug in to the input of a language model that allows the language model to condition on whatever the adapter is taking in. So it can be images, it can be audio, video, it can be any other tokens, style representing a style. The adapters themselves can be linear, can be deep neural networks, it can be low rank, and so on. That's why I hear people say more like LoRa adapters, right? So LoRa is like low rank, just saying the adapter can be low rank, which makes it more efficient. But adapter is a general paradigm. Cool. And nowadays, people also find that you may not even need to train a big adapter. It can literally be a linear projection, right? From images with an image encoder that may be big, but I freeze a big image encoder. The text decoder, language model, big, freeze it. I just train one linear projection, and that can be sufficient to align the image features with the language model features. And it can do everything that we just talked about, right? All the conditioning on the image and generate text like captions, dialogue, QA, and so on. Whether this paradigm is actually sufficient for all modalities, in fact, even for all types of images and captions, is still an open question. It's definitely making a lot of assumptions in this linear projection, right? More likely, my hypothesis is that if the connections between image and text are perfect, they're strong. Like just in many of these image captioning cases, it's literally just the image of a dog and the caption is the picture of a dog on a skateboard. If the mapping and connections are very strong, it may be enough, but it's unclear if this will generalize to modality pairs that have fewer connections, right? Think like your medical sensors and like whatever thing you want to predict in your patient. Maybe it will work, maybe it will not.
So
originally the linear was, okay. Well, one thing here is that, okay, so this adapter can be linear, right? It can be anything that brings you language model space. But once you've run the adapter, you're basically going to have a sequence of like 2 adapter tokens and your language tokens, right? Let's say there's like 2 of them and like 3 language tokens. And then those 5 tokens would then go into your language model, where cross attention, transformer, whatever would be there. right? So even if the adapter is linear, there is still going to be cross attention once you put it into a language model. Yeah. Like for example, this, right? This is kind of an open source attempt at GPT-4. Same idea, right? You have an image, it goes to a pre-trained but frozen vision model. You map it with a linear layer, and you put the linear layer concatenated in the middle of like whatever prompt. In this case, like, what do you think of this logo design? And all of that goes into a frozen language model. So the frozen language model is still going to have your cross attention and transformer layers that attend to both the text tokens and also the linearly mapped vision tokens. Yeah, I saw a question. Okay, so the linear is architecture. What you're doing to train, like for example, I'm going to get into here, how you're training it is a completely separate question. So I can define this type of architecture with frozen image, frozen language model with a linear mapping. And then the question is, how do I train it? So in this case, these folks train in 2 steps. The first step using alignment. So if I have an image and a caption, I'm going to put in the image through this thing, and the language model is going to output a caption. That's one type of training. And the second stage of training is to give it instructions, right? So actually, if I wanted to do like VQA, for example, then I'm actually going to give it a few instructions on how to do VQA. For example, the VQA image, the VQA question, they both go into the language model and output the answer for VQA. And I might give it like maybe 10 shot instructions for VQA in the second stage.
Okay, so
It's hard to say. It's not literally translating the image modality to text. Like it's not actually capturing the image. It is, to be more precise, it is transforming a frozen image feature, which may already be very semantically meaningful and close to text space, into language model input space, right? So it is doing alignment. It is doing alignment, but it's doing alignment on top of very abstracted features that may already be very close semantically. Okay. Because if you think about it, it's like a lot of these state-of-the-art vision models, they're taking the image. They are like one classification head away from classifying the image, or segmenting the image, or doing VQA on the image, right? So these visual features, once you get here, are already very close to text. They're already like containing semantic concepts. So that's why the linear mapping is going to be enough to map them into something a language model can take in. Great. Any other questions? All right. And you can scale this to adapters to basically any modality. And these folks show that you can use adapters for 3D point clouds. So for example, I can take in like a 3D point cloud of this car-like thing. I can give it an instruction, generate an image from the 3D point cloud. And in fact, these folks went one step even further, where they had an image, they kind of piped the language model outputs to image generation. So you could actually go from 3D point clouds plus the instruction to a generated image. Right. So, but essentially, the point is that these adapters can work for any modality, right? You just gotta design the right encoder, right? For whatever that modality is, you gotta find the right data. So you gotta at least give it some instructions of solving tasks and looking at that modality. Okay. Here's an example of getting these things to do generation. Where again, it's basically adapter style model, right? You have these images that go through a visual adapter. You have some captions, and you're going to put all of that into a language model to generate some text. And I can use this text to also retrieve images, right? And I can put this text into, for example, a clip-like model. Clip, as you recall, enables us to retrieve the closest images because you're learning a representation space that is coordinated, right?
one option is chase.
So you can take the output language, you get a caption, and you can generate the nearest input image. So that enables you to do things like this. You can take in a particular, like for example, image of a sushi, and I can add the word digital drawing. So the model takes in the image of the sushi, it takes in the language digital drawing. That's going to get a new caption. For example, I want the image of sushi with digital drawing, like all that is literally in text, and I can use clip to generate the nearest caption. Right? And you can actually get images of sushi in digital drawing. Right. And you can do that for dialogue as well, right? I'm thinking of a animal which is brown and furry and has a tail. What is it? Language model says a squirrel. No, the animal I'm thinking of lives in a river. Language model says, oh, it must be a beaver. And you can say, that's right, what do beavers look like? Show me an illustration of a beaver. And it can generate or retrieve an image of a beaver. Okay. Okay, we're going to stop talking about adapters. We're going to talk about something that goes more into the representation level. Adapters, they only were at the input level, right? So that gives you some control, but it doesn't really give you the most amount of control you can get with a language model. So one way is actually to open up the representation space of a language model, or any, in this case, any pre-trained model, and learn essentially a new embedding at the representation level that takes into both the original modality and whatever modalities that you want to condition on, right? So we typically call this more tuning, not at the prefix level, but at the representation level. So you can think of it as our original models embeddings at some point, and you're shifting that representation based on the other modalities. There's several ways of doing this. One of them that's more popular is called the pseudo-attention method. This one on the right, where essentially you have an image that passes through an encoder, and you get some features of the image. You have some other text that goes through the embeddings and get some representations. And you're using both the modality image and the language embeddings, and you're doing sub-attention on both of them. Right? You sub-attention on both of them so that they can actually contextualize each other before generating the output. This was pretty popular back when you could still fine-tune these language models reasonably, but now I think these are kind of decreasing in popularity because you can't really fine-tune language models, which you have to do if you want to train the self-attention layers in your language models. Another general paradigm is to condition via Bayes rule. This idea is also pretty neat. If I want to learn a model P of X given C, so for example, X, which is the thing I want to generate given some conditioning input, I can rewrite it using Bayes rule as P of C given X times P of X. Right? So P of X over here is the unconditional part that is just a language model, whatever a language model completes. And P of C given X is something that classifies what attribute I want my language model to belong to. So this paradigm with Bayes rule typically works when X is, for example, you want to generate text, but C is some low dimensional, in fact, even better if it's categorical attribute that you want to condition on. For example, C being formal or informal, right? So in this case, conditioning text on formal or informal might be difficult, but just predicting whether something is formal or informal given text is easy, right? That's just a classifier. So P of C given X is very easy. And P of X is just my unconditional language model to begin with. So what this will look like is that I may have some words, like for example, do you, prompting a language model. My language model may output a distribution over the next word. For example, want 0.3, prefer 0.3, the 0.1. That's also what my language model outputs. And I can also train attribute predictor that basically for each of the possible words that I want to predict, want, thus, and want, prefer, and thus, I'm going to predict how formal it is, right? Want is very informal. Prefer is a bit more formal. And thus, some people talk quite pretentiously. They use thus all the time. That is more formal, 0.9, right? So essentially, if I want to generate P of X given C equals to formal, I should take into account both of this. The distribution of words given just my language model originally, that's P of X, and my distribution of next words given how much I classify these next words to be formal or informal, right? So I can do a dot product. I can do like a multiplication. And finally, using this multiplication, I can then use that to reweight what my distribution of next word should be. I can choose the one that best balances what is assigned to be high likelihood from the original language model, and also what words is assigned to be very formal based on my classifier, P of C given X. So that's another neat idea of doing conditioning. So here's another illustration. The food tastes something. There's a bunch of possible words my language model may output. I'm also balancing what the language model output and which of the ones are assigned to be, in this case, positive, P of C given X. So visually, it's doing something like this, right? It has to balance both maximizing P of X, which has its own direction, while also maximizing P of A given X, so P of C given X, which has its own direction. Right. And essentially, there's ways to train this quite efficiently where you can alternate between maximizing words that output P of C given X and also maximizing words that have high P of X given by your model. All right. So that's a summary for today. Today, we mostly stick with these auto-regressive models. Pretty simple. Most of these language models are auto-regressive models are usually pre-trained. And we talked about a couple of ways of adapting them using these adapters. That's probably the most popular approach nowadays. These lightweight modules that you can stitch at the beginning so that these language models can take into account these other modalities. And this works pretty generally with images, with other modalities as well. You typically just got to find the right amount of paired data between the other modalities and text, and you're going to define the right encoder for these modalities. All right. Any questions? Great. If not, let's stop here. On Thursday, we'll talk a little bit more about actual generative models like DAEs and diffusion models and stable diffusion, as you've probably seen recently. All right. Thanks, everyone.